made me think about, what is the decision process and what has been actually statistics. As I used to say, the reason why statistics is not a part of math, the reason why information theory is just one piece, is that there is a global science which is as rich as biology, as physics, etc., which is a data science. And what is data science? It's completely integrated with the problem of decision, and it has its mathematical methods, it has its experiments, it has its practical cases, it has its theoretical theory, about exactly, it's a science. It's a full science, except that that science, was, so who are the big people? The first thing I would like to say is that the first big person in here is Mother Nature. My father used to make that joke when I was a kid, so that was, something 60 minus years ago, to say what is the most powerful computer produced in mass production by an unqualified workforce. And of course, the human brain. What's interesting is that the computer 60 years ago and the computer today are not exactly the same. But the remark is still valid today. If you think of it, if you look at a computer, let me just make a parallel between a brain and a computer. A brain has approximately in billions of neurons. Each neuron has in thousands of synapses. So we are talking of about those neurons synapses, the order of magnitude of the trillion, several trillions. But where the brain is very slow, the speed, the cycle. So the frequency is about the speed for an influx to go from a neuron to a synapse is of the order of thousandths of a second. If you compare to a computer, let's take the current GPU. We are in about thousands of CPUs. But the frequency is in gigahertz. So if I look at here, the potential number of actions per second is in 10 to the 15 here. Here it's in 10 to the 12. So there is still more power in the brain than in a silicon computer. Not exactly, because I couldn't say that every single synapse will react within a second. So there is a portion of that. But we're in a comparable space, just to see. Now, one of the jokes I do is that. Did Georges was aware that I would throw something to him? No. Not at all.
Not today.
Not today, exactly. And he reacted within a fraction of a second. So what does that mean? That he had pre-canned in his brain the possibility of an object going through him, and that was not foreseen. It's just something that you pre-canned. So that if you ask any machine learning computer, etc., how long does it take between the moment where the computer reacts to something, which is unexpected, and does it take a fraction of a second? And we are talking of a computer that works at that speed.
You better react that
No, no, exactly, exactly. So real life forces you to react that fact.
Well,
And yeah. So what does that mean? Well, it's a whole relation between the data world and the decision world. And now I've heard, words like duality, etc. I know one definition of duality in math is you have vectors and linear forms. So you match like you have portfolios and prices. In here, you have data, information, and decisions, questions. And you have, so you receive information, you have to make a decision for some reason, for some target. So let's make a bit of history. 19th century, who do we have as in 19th century? There's one big guy, Bayes. We could add Pareto, people like this. But basically, Bayes said, I have a prior, I have data, and I create a posterior with some uncertainty. I have a decision to make. Well, decision under uncertainty of inputs and uncertainty of distribution. Then 20th century was a century where we had to be industrial. Has always had, everything had to be neat, etc. Very mathematical. It was a century of Bourbaki, was a century, etc. So there was a regression. Who did we have in here? Big name was Fisher, Rao, Kramer, people like this, and the reign of something called MLE, maximum likelihood. And something that killed statistics for a century, the idea of unbiased estimator. If you look at all the papers in statistics, the first question is your estimator biased? That's totally stupid. Why so? Because if X is an unbiased estimator, f of X, well, sorry, if, let's say, X hat is an estimator of X, then f of X hat, if this one is unbiased, and f of X hat is an estimator of f of X, but this one is biased by definition, as soon as f is not linear. It cannot be. The problem is that you'll never see something like this. It will always be, we have a process where we determine some estimation of the distribution of the random variable, and we want to know some decision that depends on some other places of the random variable. Risk management is a typical case. I mean, Bill Chadwick was talking about that. You know, when you estimate that, your decision depends on that part. But the uncertainty on the distribution, the relative uncertainty, that's why I was talking about, you know, the renormalization group, where you rescale this by, so that the conditional distribution here becomes 1. The relative error on the probabilities is, you know, even if you don't know whether it's this probability or that one, etc., with certain uncertainty, the relative error is huge. It's becoming like this. So the relative error in the center is acceptable. In the tails, it becomes enormous. So this is a weakness of all this process. What is its strength? Why did people do that? Because it's something very comfortable. How do you do? What's the next step? Utility, decision. What do you do in here in this process? Well, as I told you, we had data, decision. Now that's the real duality here. And from the data, we get some information, so distribution. And from the distribution, we get, now we can take any decision once we know the distribution. And of course, this decision will be, you know, like Jamie Dimon, who said it is a 1 in a 40 billion years event. Why? Because he's in this level of uncertainty here. He doesn't know whether it's 40 billion years or 3 days. So we have, you know, you need to take some decision, but when you make this process here from data to distribution, you don't care about which decision. You just, you know, say, okay, well, now that I have my distribution, I can evaluate my utility and take a decision. So I can make the whole start of the process without bothering about what question I'm going to ask. Now we go to 21st century. What's 21st century? We drop the ML. What is machine learning? You put it the other way around. You first start from the decision. What do I have to decide, this point? Well, let me see here what all my data will tell me about that point. So here you start from the question, learn. So what is learning? In some sort, it's an optimal use of the data. Agnostic use of data for a given question. And then I get, you know, an algorithm, a process, to make a decision vis-a-vis that particular question. Is it a cat or a dog? The reality is complex because now in George's brain, if we have that we need to have billions of such questions like this so that he's been prepared to a chalk, he's been prepared to something else, you know, the beautiful lady, and he's very sensitive to that, etc. So you see the number of questions that we may have in here to machine. And that is a major limitation of machine learning. Machine learning is well adapted when you have a finite set of questions. AlphaGo, Deep Blue, etc. A bit more complicated when it's about doing a self-driving car. Because a self-driving car has to deal with all sorts of possible situations which are kind of categorized. So now we come to actually how the system works. Let me erase some of that. So what do we need actually? What are we missing? We don't have a single point here. In a game like AlphaGo, like Go or chess, we have a very given set of points, and we can address that. The rules of the game are determined, and we can address that. In real life, it's much more complicated. So we need some sort of topology on that set. We need some structure so that we can say, I'm not ready for that particular question, but I'm ready for a range of questions that correspond to certain things. That's actually, if you think of it, all those robots that we have in the brain are essentially prepared for what is focusing the most risk management. And risk management are events that are extremely rare. But we are trained, not like a computer. The other thing that, I raised the comparison between computer and brains. When you do machine learning, when you train a machine, how many instances do you train the machine on? Is anyone doing machine learning here?
Many.
Well, we are talking of anything between hundreds of thousands and a few million. That's the order of magnitude. Bruno, do you confirm?
Yeah, it's 3.77 million.
Yeah. How many chokes George has received in his life?
Over here, many. Not chokes, but similar chokes.
So, yeah, basically, we are doubly trained. We are trained like with billions of situations where we receive a choke, and we have to react. Why do you think puppies are playing and babies are playing all the time, etc., testing? This is a training, it's machine learning training. Second, we are trained with billions of years by Mother Nature, by the fact that our brain has been created this way. So the level of learning that a biological brain gets is in no way comparable to the level of learning that a physical silicon computer may have. Just no way. This is a different order of magnitude. So what does that mean? We have time to create a structure on the whole sets of questions that we may have. I said, he doesn't care whether it's a chalk, it's a stone, or whatever. He just sees an object coming. And that's enough. So he has categorized the thing. So that means that when we have some data, the first thing we do is that we do a level of feature extraction. So that's a step which is very standard in machine learning. Even today, people do feature extraction. Just to do image analysis, people do they will extract the contours and see whether, if you think of a system that reads automatically, you see a picture, you need to see that there is some place where there are some shapes that could be identified as letters. Then you have to identify that they are letters. So which letter? And then once you have identified which letter, in which alphabet they are a letter. And then those letters group into words. In which language those words happen, in which dictionary they pertain. And then do they make sense? And those sense, when you see something, you read, it has to pass a message, whether it's a constitute a sentence or something, they have to pass a message. And again, is that message useful? Is it just advertisement, or is it a warning that you have to react to, etc.? You see the number of layers that we do to analyze what we call feature extraction. We can do that through machines. The question is, what is the set of feature extraction that is the most useful? Can we optimize that process? That process is in several layers. Can we optimize? That's where information, measure of information in the Shannon sense comes. But in order to say that I extract this feature that is rather than that other feature, I extract a feature that will maximize the information it gives. I need to measure the level of information it gives with respect to what? With respect to our set of questions. That's why we have a topology. Because we say, I want to have a subset of questions where some are likely, some are less likely, and I want to answer this category of questions. I'm not saying nothing is easy in what I say, but it is basically the type of thought process that we have to put in place to come up with maybe someday some computer that will resemble and or approach the decision process of an actual brain. How to define entropy in here in the Shannon sense? I think the best way I have to define it is the following. You, okay, take the set of all possible pictures that you can create. So you get, it's like a big vector of pixels with intensity with different colors. So it's a very large vector, dimension several million, and intensity of each pixel. If you take a vector at random, what will happen? The probability that this vector, that this image is even something that has, even the shape is very, very, very low. Most of the time, you will see something which is just a completely random dots of different colors. Within those who make sense, those who have a shape where you can recognize something, whatever it is, abstract art, whatever, is again a very tiny subset. And within those who represent, let's say, an animal, is again a very, very tiny thing. And the fact that this animal is a cat or a dog is even tinier. So you see that when you do a machine learning question and you set the question, now you can count the number of 9 that you put 9999999%, that there is no answer to the question. And this is where the level of information. In some sense, if you look at the number of pixels and the number of possible images you can create with a certain number of pixels, this is, n is the number of pixels, so it's, it will be some alpha to the n. But the number of images that represent something will be some beta to the n. So the level of information by simply saying this is an image is log of alpha. The information is log alpha over beta. This is what you have brought as an information by simply saying this is an image. By saying this is an image of an animal, the information is log of beta over alpha, over gamma, etc. This is what information is. Just take the reverse and you call that entropy. So in some sense, you want to have feature extraction so that instead of having raw data, I have those features will help me answer those questions by maximizing the level of information that it says by saying, okay, I have this feature rather than that feature. Now, last thing about that, there are situations where the topology is quite easy. And that's why I realized, because when I created the theory of those polymodels, etc., I didn't realize I was doing that. If you ask the question of having a stress test, you have any asset you want to know. So what is a stress test? Basically, you have a system, which is a complex system, Y subject to some environment, which can be described by a big vector, capital X. And then you want to see what the conditional expectation of y given x. So that means you want to be able to move x and see what the impact, what's the expected impact on y. And you want to find that function of x. Then you will put a certain topology here, and that can be, some sort of, I wouldn't call it a Euclidean topology, but it's still something that, there is no dynamics. So you need to extract in X what are the directions that make sense. People call PCA, etc. Forget, doesn't work that way. But you want to extract the most meaningful things. So that will be some kind of extreme analysis to know where you are going to extract the topology. And you get a topology that looks like a topology. And then you try to define sensitivities, etc. So this will be, the most efficient feature extraction for a stress test type of question. Much more complex comes where, in fact, what we have when I throw is that he sees, in fact, he has a very fast assessment of the trajectory of the thing. And he knows that there is a range of trajectories that is likely to end into his body. So he has to move. Why is it so fast? Because what is pre-canned here, it's not it's a simulation of the dynamics of the environment. So we have pre-canned not xt, but some dynamics of xt. And we match that immediately on the possibility, and we automatically process to the future. Another situation which is even more complex is you want to hire someone, you see someone, you want to know whether you can trust, you have just a few seconds to know whether you can trust someone or not. And how fast do you go? Well, again, you have some pre-canned models, and you try to see, and what is the usual model for a complex system? It's not a simple dynamical system like this. It's a cellular automata, usually. And then you simulate the future of that, and you see whether that corresponds to that. Is it, this kind of animal or that kind of animal? That you will, so that we have pre-canned, in fact, dynamic simulations. So that's where the topology becomes more complicated, because it's what I call, a butterfly flap topology, in the sense that you have a system where to say that A is close to B, you make them evolve, and you say A is close to B if AT and BT look alike for some time at a macroscopic level. Not necessarily very fine level, but the longer they stay alike, the longer, the closer A and B are. So basically, you look at the subsheets of finite type, and you see how long that stays on the same thing. Well, basically, that's just the pictures that the method that I think people should do if you want to go one step further in data science and machine learning. Thanks.
Thank you so much.
So let's